Alright, so yesterday we started the unit over acids and bases, and we talked about what makes an acid and what makes a base, and then we talked about the fact there are strong acids that completely dissociate, and there are weak acids that only partially dissociate. And then we started talking about the idea of pH. And the thing that makes an acid is hydronium, or water with an extra hydrogen. So the way that we find pH is to take the negative log of that hydronium concentration. And if you know anything about logs, you know that the higher the number, the lower the log, basically. And the lower the number, the higher the log. So the pH scale goes from 1 to 14, where 7 is neutral, and less than 7 is an acid, and greater than 7 is a base. So finding the pH from the amount of hydronium that you have gives you an idea of how acidic something is. The lower the pH, the more hydronium there is, the more acidic it is, or whatever. So pH, really and truly, we know about it in chemistry, but the pH scale was made for like the everyday person, so that they can find the pH of their pool and know if it's too acidic or basic. And for people who work in like chemical factories and things like that, so they can test the pH and have a readily available scale from 1 to 14 that makes it very simple to tell if it's acidic or basic. As chemists, we need to know more. We need to understand the relationship between pH and hydronium, and it's the hydronium that we really care about. So, there you go. pH is kind of arbitrary. Even more arbitrary is the pOH, which is the negative log of the hydroxide concentration. Same thing, 1 to 14, where 7 is neutral. But now less than 7 means it's a base, and greater than 7 means it's acidic. The more hydroxide something has, the more basic it is. Questions so far? Okay, so for a strong base and a strong acid, to find the hydroxide and hydronium concentration, we're just going to use regular old stoichiometry. Just plain old stoichiometry. Moles to moles, or liters to moles, moles to moles, moles to liters. Find the concentration, find the pH or pOH. For a weak acid and weak base, it's going to be more complicated, and we'll talk about that later. But strong acid, strong base, just use stoichiometry. Find the concentration, take the negative log. Because of the way that pH and pOH scales are set up, they're like supplementary or complementary angles in math, where they add up to be 14. So if you know the pH, you can find the pOH, and vice versa. If the pH is 1, the pOH is 13. If the pH is 7, the pOH is 7, because neutral is neutral. Right? Okay. All right. of all of the things that I teach you in AP Chemistry, this one usually produces the most anger.
No, don't say that.
If we take water plus water, what do we get?
Water.
Unfortunately, no.
Oh.
We get hydronium and hydroxide. So, what this reaction is trying to demonstrate to you is that a glass of water, pure water, not Wabash River water, is not in fact just water. It is slightly ionized, meaning some of the water molecules have reacted with each other. Some of them have donated a proton to the others, and you've gotten some hydronium and some hydroxide. When you drink a glass of water, you are drinking some hydronium and some hydroxide. Water is both acidic and basic. We talked about that yesterday. It's amphoteric. It can behave as an acid and it can behave as a base, depending on who it's hanging out with. That's all because of this, because it has both ions present. It has the properties of acids and bases, depending on the reaction. So we have a new K. Kw for this reaction, the only reaction, is the concentration of hydronium times the concentration of hydroxide. And at room temperature, Kw equals 1 times 10 to the negative 14th. What does that tell me about this reaction? Does it lie to the right or the left? Way to the left. So that glass of water is really and truly a lot of water. And just a little bit of these two. But when we're talking about pH and acids and bases, just a little bit of those can have an effect on the pH. And if we did this and we found the hydronium and hydroxide concentration, aren't these equal? 1-to-1 ratio? I could just take the square root of this to find out that they both equal 1 times 10 to the negative 7th. The square root of 1 times 10 to the negative 14th is 1 times 10 to the negative 7th. And then I could find the pH of water. Right? I have the hydronium concentration. What's the negative log of 1 times 10 to the negative 7th? You're going to learn something about logs. If it's 1 times 10 to the something, the negative log of this number is always just the positive exponent. As long as it's a 1. If it's something else, that doesn't work. You have to type it in your calculator. But if it's a 1, you can just use the exponent. So what's the pH of water? 7. Is that surprising?
No. Whoa.
Whoa. What's the pOH of water?
7.
7. Is that surprising?
Also not.
No. That's all because there's hydronium and hydroxide. They're equal. And their concentrations are fairly low. 1 times 10 to the negative 7th moles of these per liter of water. That's not very much. Make sense? Okay. Stoichiometry is great for strong acids and bases, things that completely dissociate. For weak acids and weak bases, we'll talk about those later, they do not dissociate completely. You wind up with equilibrium. And to find the pH of a weak acid, I have to use an ice table to find the hydronium concentration. Right? So for this reaction, I would take Ka, this is A for acid, another K to add to the list, equals hydronium concentration times hydroxide concentration divided by the original acid concentration. And if we look at this table, you see that you start out with X, 0, 0, just like before, minus X, plus X, plus X. You don't necessarily have to write this down, but, and then you have X and X, these are equal, and then big X minus little x. And if you left it like that, you would wind up with a quadratic. And we know that we don't do those. But we also know that these are very weak acids. They're weak. So little x is going to be much, much smaller than big X. And it's negligible. And we can leave it out. We don't need to subtract. We can always just plug in the original concentration of the acid, whatever it was. 0.1, 0.05, 0.001. You just plug in that molarity. And then, because these are equal, oh, this should be A minus. I'm sorry. Because these are equal, change that to A minus if you wrote hydroxide, because I'm dumb. We only care about hydronium because we're always going to be caring about how strong the acid is. You're going to see it like this. Hydronium squared over the original acid concentration. This is the one that will be the most useful to you to solve for hydronium and find the pH, or the strength of the acid. Rylan?
Is that for the positive equation?
Yeah.
Why would you square that?
Because these are equal,
Okay.
and we really don't care about this concentration, we care about this one. But they would be the same either way. Hydronium and hydroxide are the kings of this unit. They're, or queens. That's what we care about.
Yes.
Questions?